Hello grade 12s. This is a revision of integration techniques that we have done so far. There's a lovely summary on page 91 which also gives an idea of how to approach different integration sums, because one of the biggest tricks is trying to discover which one of the many techniques it is that we have to use. Okay, so if you go to the textbook on page 91, you'll see it gives you a table over here, and in that table it tells you the types of expressions that need to be integrated, examples of them, and the method of integration. So we're going to try and do one of each of these ones. So the first one is simple variations of your standard type. So your standard type are the ones where you can use your formula sheet, where you just simply go from right to left. So if you want to integrate cos of x, it's going to be sine of x. If you want to integrate sine of x, it's going to be minus cos of x. Now they are simple variations, and the reason they say they are simple variations is instead of just going cos of x, they might go cos of 4x plus 1. But these are called simple variations because the inside of that function is going to, the derivative of the inside of that function is going to be a constant. So the moment you have any of these ones, and inside those functions, inside that x there, they'll put 2x, so the derivative is 2, which is a constant. Or inside over there, they'll put 4x minus 3, so the derivative is 4, which is a constant. You can use this shorthand, or these simple variations of the standard type. So in the first example, it says the integral of cos 3x. So cos, according to this table, is then going to be integrated into sine. So I will then just say it's sine of 3x, and then you use that short method where I divide by the derivative of that inside, which is 3 plus c. And I'm done. Simple as that. So these are just the variations on those simple ones where you use the table. The next one is a product of two expressions of the form the derivative of gx times gx inside fx. Now this is the one that we refer to as the reverse chain rule. So you have the compound function, and then the inside function's derivative is being multiplied by that compound function. So that would be something like the following one. So if you look at the following one, you realize I have a compound function over here, and I'm going to just rewrite that as cos of 2x to the power 4. So there's my compound function. So then my question is simply, can sine of 2x be the derivative of cos of 2x? And if you look at it, you say the derivative of cos x must be negative sine x. So I can fix that. So I can fix that saying this needs to be negative sine of 2x, but because of the 2, using my chain rule, this needs to be 2 there. So simply put, if I find the derivative of cos 2x, can I manipulate what I'm multiplying by for it to make it exactly the derivative of that inside function, which I've now done. But please remember, once I fix that inside function, I have to fix the outside, so I have to put minus a half, because obviously minus a half times minus 2 gets me back to that. So this is then the derivative of the inside function, which goes back into the Russian doll. It disappears. We don't see it anymore. And the inside function, I don't touch it. Remember, nothing happens to that inside function. The only thing that happens is that outside function gets integrated. So this is going to be cos 2x to the power 5 over 5. And then remember your plus c, so if I clean it up, it's minus cos 2x to the power 5 over 10 plus c. So that's the reverse chain rule. That's reverse chain rule. By the way, you could have done this one with reverse chain rule as well, but we can use that little shortcut that I've shown you before. Now the next one that they talk about is they talk about products of the form x times e to the power of x, or x squared times sine of x. Now these ones specifically are my integrating by parts. So that means we have that compound function, but the derivative of the inside function is not going to be what's multiplied by the outside. Okay, so an example of that one would be this. So for this one, I have to go and I have to set fx, normally, except with ln x, we did do that in the previous video, equal to the simple one, which is x. Just write set there. And we're going to set the derivative of gx equal to that compound function, which is e to the power of 2x. I then find the derivative of fx, which is 1. and then I find the integral of that, which is gx, and the integral of that is going to be e to the power of 2x over 2. Because remember, if I find the integral of e, it stays e, but because of that simple form that we've just discussed, we don't multiply by the 2, which is the derivative of 2x, we divide by 2, which is the derivative of 2x. Then I sub it into my integrating by parts formula, which is that times that. Minus then the integral of that times that. So I can take the half out as a common multiple. And they even remind me to put the plus c that is on your formula sheet. And then I can just finish it off by doing this exact same integral again, which is what I did over there. So I already know what it's supposed to be. And then I can just clean it up by multiplying that 2 by 2 and making it a quarter. Okay, so that was pretty easy and straightforward. Then the next one they ask you to watch out for is the following one. This one specifically talk about quotients of the form the derivative of fx over fx. So the moment you have a quotient or a fraction where the derivative of the denominator is potentially the numerator, and you can fix those as well, then we're going to use inspection of the rule ln of the absolute value. Please remember that absolute value. So in this case, there's a fraction. The denominator is x squared, the numerator is x, which means this is potentially the derivative of the denominator. But I'm going to have to fix it because obviously the derivative of x squared plus 1 is 2x. I have to fix that. So because I multiplied by 2 there, I have to multiply by half there. Just don't forget your dx to clean it up. Now, the numerator is exactly the derivative of the denominator. And that's why I can then use ln. And remember, it's ln of the absolute value of x squared plus 1 plus c. So those are the ones where you have the derivative of the denominator inside the numerator, or if you can at least adjust it, then you're going to use ln. Right, the next one is then polynomial quotients which may be split into partial fractions. Now, before we do these ones, I did forget to do one example in the previous video on integrals involving natural logarithms. And I thought, let me just put it in here since we've just done one of these ones. Now, these ones are not exactly obvious at first as being one of those integrals involving natural logarithms because it's slightly in the wrong format. We have to fix it algebraically first. And to fix it algebraically, I'm going to do the following. And this is something, unfortunately, you're going to have to go and look at quite a few of these and just try and memorize this format to recognize it. So what I'm going to do to manipulate it is I'm actually going to take out the square root of x as a common factor here at the bottom, or x to the power of a half. Now I know, and I'm fully aware of it, that it's not a common factor. I'm very, very fully aware of that. But I'm going to manipulate it in such a way that it is. Meaning, if I have x to the power of a half as a common factor, over here I'm going to have plus 1. But hopefully you guys will be able to spot that if I take x to the power of a half out there, I just need to put x to the power of minus a half over there. Because x to the power of a half times x to the power of minus a half means it's x to the power of a half plus a half, minus a half, which is 0. And x to the power of 0 is equal to 1. So I manipulate it in such a way that it actually works out like that. Then what I can do is I can do the following. I can then go and I can move this up to the top. I think I've messed this one up. Welcome back. Yes, I know the end of that before I restarted the recording in was pretty much me going, I think I messed that up, and I did officially mess it up. If we look at the example now it is correct. It was not supposed to say 1 over 1 plus the square root of x, it was supposed to say 1 over x plus the square root of x. So my apologies, I just figured let me correct the mistake rather than restart the entire video. Okay, so again, this one is an integral involving a natural logarithm. At first, you can't actually spot it until you manipulate the bottom and you say, I'm going to take x to the power of a half out as a common factor. Now this one's slightly easier than what I was doing before I stopped the video and corrected, because now if you think about it, this is going to be x to the power of a half plus 1. Simply because x to the power of a half times x to the power of half is then going to be x to the power of 1, because a half plus half is 1. Then x to the power of half times 1 is then going to be square root of x, or x to the power of a half. Now I can go and I can move this x to the power of a half up into the numerator. But please remember, if you move it up into the numerator, you get a negative exponent. And now hopefully you'll see why this is in fact one of the integrals involving the natural logarithm. And that is simply because of the fact that the degree above is 1 less. So the degree in the numerator is 1 less than the degree in the denominator, which then means that this is in fact, or could potentially be, the derivative of the bottom. So obviously we're going to have to just adjust it by saying the derivative of x to the power of a half is supposed to be a half x to the power of negative a half. And because I had to multiply this by a half, over there I need to multiply by 2. Okay, so now the numerator is the exact derivative of the denominator, which means I can then just go and say it's the ln of the absolute value of that bottom. Now I'm just going to rewrite that as square root of x plus 1. So these ones, I've never seen them before, in all honesty, just because they are very tricky and they are very difficult to spot. But I figured let me just show you this example. You'll see in the textbook on page 88 they actually do this by means of a U substitution. So you can try the U substitution method if you think that that's maybe going to be a little bit easier. I think this is pretty easy and straightforward. I'm not a fan of U substitution, but you can try, look at the example on page 88 and see if you like the U substitution, if you understand that a little bit better. Okay, right, next. So we've discussed quotients of that form. We were busy talking about polynomial quotients which may be split into partial fractions. And when we did the revision of partial fractions, and when we did these ones where you first have to go and split it up into a partial fraction before you find the derivative, I did tell you I think they will scaffold it. That's what they did last year in the final exam, where they will first ask you break it up into partial fractions and then subsequently ask you to find the integral. So please just remember, this is a pretty easy and straightforward partial fraction. X over 4, x plus 4 over x times x minus 1 is going to be a over x plus b over x minus 1. So we're going to multiply by the LCM of the denominator, which means x plus 4 is going to be a times x minus 1, and then b times x. And then we're going to set x equal to 1 according to the cover-up method to cover this up. And then we're going to set x equal to 0 according to the cover-up method to cover that one up. So if I set x equal to 1, this is going to be 5. This is going to be 0, so that goes away, but this is then just going to be b. So b is equal to 5. If I set x equal to 0, this is going to be 4. This is going to be a times 0 minus 1, which is minus 1. That one's going to get covered up, so in this case, a is then going to be equal to minus 4. So that means I can then go and rewrite, sorry about that, I can rewrite this particular integral, and I can say it's then the integral of a, which is minus 4 over x dx, plus b, which is 5 over x minus 1 dx. And then hopefully you guys can see this is one of the type where the derivative of the denominator can potentially be the top. If, in this case, I just take the negative 4 out as a common multiple, and I've got 1 over x, which is a very simple integral to do. And over there, the derivative of x minus 1 is 1, so again I need 1 at the top, so I'm going to take 5 out as a common multiple. And then I can just go and say this is minus 4 ln of the absolute value of x, and this is going to be plus 5 times ln of the absolute value of x minus 1. We have done quite a few of these ones. Please remember your plus c. So these are the ones where you will probably be asked to do a partial fraction before you're asked to do the integral. Right, now the next one, they specify odd powers of sin x or cos x. Now we have done examples like this where they say use the identity sin squared x plus cos squared x and then write it in this format. And that format is your reverse chain rule. So if I get something like this one, which is the integral of sine to the power of 4x. Sorry, sine to the power of 5x. I'm going to rewrite this one, and I'm going to say it's going to be equal to sine to the power of 4x, just write it like that so you guys can see it a little bit better, times sine of x dx. Now, a lot of people don't seem to understand, but if sine squared x is 1 minus cos squared x, okay, so let's write it down over here. Then I can go and I can rewrite this and say sine to the power of 4x, which then means I need to square the left-hand side, so I need to square the right-hand side. So I can then go and say it's 1 minus cos squared x squared. So I can do that. Now, this one does continue on quite a ways. I have actually done one of these in one of your homework exercises where I did all of that. So I don't necessarily want to continue all the way through with this one. I will write it out so you can look at it in the notes, but I'm not going to actually do this because, again, otherwise these integral videos get very, very long. So I will continue with this one in the notes, but I'm not going to continue with it over here. Also, I've hardly ever seen any of these. Okay. What's a little bit more important are these ones. And these ones are the ones where you have the even powers of sine x or cos x. You have the same angles or you've got those different angles. So these are pretty much the ones where you have sine x, cos x. And I have done these to great extent in your trig integration. Trig integration is quite a lot. But I want to do this one specifically because this one was an IB 2017 exam. So first things first, we recognize you've got sine x plus cos x squared. So I'm going to have to do the algebra first. And I'm going to have to say that's then going to be sine squared x plus 2 sine x cos x plus cos squared x dx. There you go. Now, hopefully you guys will see that I can then take sine squared x plus cos squared x and I can say that's equal to 1. That's part of those whole identities that's so important with trig integration. So I can change that to 1. And then hopefully you guys will see that 2 sine x times cos x is then the double angle formula for sine x. So that's going to be the sine of 2x. And then, good news, because there's a plus in the middle, I can say it's the integral of x plus the integral of sine 2x, which is actually very simple to do. The integral of 1 is going to be x. And then the integral of sine 2x is one of those standard integrals. Careful though, sine 2x becomes minus cos 2x, but I also have to divide by that 2. And that's why the plus and the minus will just end up being a minus. Okay. So that's pretty much revision. You do have to sit and you do have to go and practice it. This is pretty much the only way you're going to get good at integration, is to sit and practice, and also that's the only way you recognize which of the techniques you're going to use. So the next video, which will be only next week, will involve practical applications of your integration. Thank you very much for listening.